In this figure, you can see in this figure you can see different regime where you can have different decay processes. Okay, so this is nothing but the number of neutrons versus number of protons uh, graph. So this is that is nothing but number of protons. Okay, this number of protons, and in this y-axis we have number of neutrons. So we can observe that when the number of neutrons increases, when the number of proton increases, that is along x-axis. This is along x-axis. When the number of protons increases along this x-axis, there is number of neutrons which is also increasing in the y-axis. Okay, so if you consider the same number of neutrons and protons, for example, we can see from here 6 number of neutrons, number of protons, and 6 number of protons. We have this point. Okay, and if you consider in this particular case 28 number of protons and 28 number of neutrons, then we have this point. And if you have some 82 number of protons and 82 number of neutrons, this is 82. So this you can have different points, and if you join those points, then you will get a straight line like this one. Okay, so that is where you are having this straight line. This is where you are having your n equal to z value. So this is highly stable. When n equal to z, these are highly stable. And there are some deviation. There is some deviation from this curve, that's from this straight line. When we observe the experimental results, there is an increase in number of neutrons as compared to number of protons. We can see that the this graph, which is going initially, it is in the same straight line, but when it is having large number of protons, it is going away from this straight line. So this straight line, this is the straight line with n equal to z, and the experimental result shows that the number of neutrons increases when more than number of protons when we have more mass number. So which means that if you are having n equal to 28 here and n z, you are having some values for neutrons, then sum of these two, that is neutrons and proton, will give you mass number. So if you consider higher mass number, which means that somewhere here we can see that the number of neutrons are larger than number of protons. In this curve, number of neutrons are larger than number of protons. We can say n is greater than z. I should see a small line here. Okay, so that is what we have observed experimentally. When you increase the mass number, you are having when you are having higher nuclear size, or the nucleus is which is larger, then you can have a deviation from this straight line. You can observe a deviation from this straight line, and you will be having this condition, that is the number of neutrons will be larger as compared to number of protons. Why this is happening? This we already discussed a little bit. So when you are increasing, for example, in the case of helium, if you consider the case of helium, which is very small, so this is having how many? 2 protons and 2 neutrons. So this is an example when you are having your Z, which is equal to N, that is number of protons equal to number of neutrons. So in this case, the helium will be in this line, in this straight line. Okay, helium nucleus. So it is its mass number is 4. So it is in the initial stage of the spectra. This graph. Okay. So it is having equal number of neutrons and protons. But when we go for higher nucleons, higher nuclei, then we can observe that there is an increase in number of neutrons as compared to the number of protons. Let's take this example. So you can observe from here. This for example, this is 50. Is at 50, and this is at 82. So we can see that this nucleus, which is at this point with some mass number, which is having n value. Let's take in here we have the n value, which is 82. That is number of protons, and you have number of protons. Sorry, number of neutrons is 82. The number of proton we have 50. So n is very large than this number. So when it increase, and if you take the sum of this, you will get the mass number. Okay. So this will be 132 A, which is A equal to 132. So this is the nucleus with the mass number 132, which will be having a proton number equal to 50, but neutron number equal to 82. So when you increase the mass number or the size of nucleus is larger, this deviation from n equal to z is larger. So this is because we already discussed a little bit. So when you are having this, and if you are having more number of protons inside, okay, more number of protons, and you are having some neutrons also. So when you are having very large size nuclei, then the interaction between these adjacent nucleons, that is between proton and neutron, will be through the nuclear attractive force, okay, through nuclear attraction, and it is very strong attraction. But when you are having very large nucleus, if it is small, then it is not a big issue. When you are having large nucleus, this neutron will be attracted with the neighboring neutrons and protons like this. Okay, this is just an example. So this neutron will not interact with this neutron or this proton. So it will only interact with the neighboring nucleus. That we already discussed when we discussed about the nuclear force. So nuclear force is a short range, and it is acting between these neutrons, these nucleons only, neighboring nucleons only. It will not interact with the other nucleons. Similarly, this neutron will interact only with these nucleons. This proton interact only with this its adjacent neighboring nucleons. So it will not interact in the any far nucleons. But for the case of protons, if you are having more number of protons here, okay, then this proton and this proton can interact. This proton can interact through Coulombic interaction. Okay, that is through electrostatic force. These protons collectively can interact with this proton, okay, through Coulombic interaction. So if you're having large number of protons, then all those number of protons can interact with a single proton, and which this will cause a very high repulsive force in the nucleus. Okay, so in order to avoid this Coulombic repulsive force, nucleus itself will try to increase the number of neutrons. It will try to now increase the number of neutrons, and it will produce more attractive force, more nuclear attractive force inside the nucleus, and it will try to reduce the number of protons and the interaction, that is the Coulombic repulsive force. So that is why this there is a difference between neutron number and proton number. So proton number should be less, because there will be some Coulombic repulsive force inside the nucleus because when we are having more number of protons in the nucleus. So the nucleus itself will try to increase the number of neutrons when it is having more mass number, and it will suppress this nuclear repulsive, sorry, Coulombic repulsive force. Okay, so that's why there is a deviation when you are considering mass number which is larger from the n equal to z line. And we can also see that there is a quasi-stable, or we can say a stable curve in between by this black color. This is also stable, but this is highly stable, n equal to z. And when you consider this case, okay, where we have let's say like this is having same number of neutrons. Okay, so if you consider this line, so all these nucleons, these nuclei having same number of neutrons, and they are called as isotones. And I hope you know that. So these isotones, which means that they have same number of neutrons, that is 50. All these nucleons are having nuclei are having same number of not neutrons. And if you consider protons case, these mass number or nucleons will be having same number of protons. It is 50 here. Okay, so they are isotopes. So when you consider these isotopes, for example, if you consider these isotopes, there are 80. For example, this case, this is 82 is the number of neutrons. Okay, but the number of protons are 50. And this blue color which shown here, which are unstable, which are not that much stable, and this color which is yellow, you can say the dark yellow, which is also um, not stable, but in between there is a stability in this black curve. Okay, these are stable nuclei, or we can say these are the stable isotopes, because in this isotopes, if you consider these are the isotopes, then this is the stable isotopes line. Okay, so when you consider these isotopes, then the nuclei which is above this line, this stability line, they will try to come into this line. Okay, similarly, those nuclei which are below this line also comes towards this line, as you can see from here, in order to have the stability. They will try to come into this line. So in the first case, we are having more number of neutrons here in this portion. So in this blue curve, we are having n greater than p, so which implies they will try to convert neutron into proton and reduce the number of neutrons, increase the number of protons, and they will come towards this line. Okay, they will try to come to this line. Similarly, in this region, they are having uh, less number of neutrons. Okay, so and in this case, in this particular case, they are having less number of neutrons. For example, you can see here as compared to the stability line. So here the only possibility is that they have to convert this. For example, if you consider this particular point, they have to move this direction. So they have to move this direction. Okay, in order to be in this line. So what they will do, they will try to increase the number of neutrons and go in this line, or as well as reduce the number of protons here. So they will try p to n, and they will try to be stable. Okay, so in this regime, in this blue curve, we are having conversion from neutron to proton, because we have excess of n, Here also we have excess of n, but we are having the stability line which is above, so they have to reduce the number of protons to reach in this stability line. So this region will be beta plus decay. So when you are having a proton which is converting into neutron, which is called as beta plus decay. When you are having neutron which is converting into proton, and that is beta negative decay. Okay, that we will discuss later when we discuss about the beta decay processes. So this is a quick review where this will happen. Okay, and you are also having alpha decay that we are discussing now. So the alpha decay will happen in these yellow colors. So in these regimes where we will be having more number of uh, size is larger, and we are having more number of nucleons, and the nucleus tries to reduce the number of protons by changing that into some different nuclei, that is alpha nucleus, sorry, helium nucleus, and that will come out of the nucleus. Okay, it is also same concept. So for example, if you are having a scenario like this, a big nuclei, a big nucleus, so it will try to for example, it will try to catch up these two protons and these two neutrons. Okay, so they join together and come out. So this will be your alpha particle. So it will try to reduce the number of protons so that the nuclear, sorry, the Coulombic repulsive force will be reduced and the nucleus will become stable. So that is alpha decay, and it can be possible, it can happen in this regime that is in yellow color, you can see. And there is also fission process that will happen for heavy mass regime in this green color, especially for uranium, thorium, like heavy nucleus. And we can also have the proton decay, the proton emission that is in this region. We can see very slightly, very small. And neutron also we can see from this line, this regime, that is neutron decay, and this is the stability line. So that is the whole process of decay that is happening in nucleus, and you can understand from this curve what is where is the region where we can observe this beta decay, beta negative, beta positive, and alpha decay. Also fission reactions, fission and proton, all those reactions. From this curve, we can observe where it can happen. So the beta negative decay will happen in this region. They will try to convert number of neutrons into proton and come to the stability line. And the beta positive decay will happen in this region. They try to convert the proton into neutron and comes to the stability regime. Okay, stability line. And alpha particle also, which is in this regime, they also try to uh, reduce the number of protons to be in this stability region like this. So they will try to reduce the number of protons, and they will go in this direction and be in this stable position. So that's all about the decay processes basics from the neutron proton curve. We'll continue the gamma theory. So before that, where is this? Okay. Okay, now we'll consider the gamma theory. We'll continue from the last class. So we reached in this expression ln of t equal to minus 2 to L. So we already reached here, and with limit r0 to r. So we didn't. We should not we not take any limits in these steps. Okay, so that is very important. So we just integrate, and we apply the limits only when we reach this step, because this is the step where we have all the parameters in your R. the variations in your R. Okay, so then you have to substitute these limits R0 and R. So we'll start from here. So the final result, not the final result, the last result we got that ln of t, that is the transition probability. So ln of t was which is equal to minus 2 times 2m 2me by h cross square all raised to 1 by 2 into r times will be sine inverse of r by capital R plus root of r by capital R into 1 minus r by capital R, and we have to apply the limits r0 to r. So this r0 to r we already discussed from this curve, that r0 to r will come like this. If you draw, then this is your r0, and this is the point where you are having your r. So the wave function is coming like this, and it is decaying exponentially, reaching this point where this point is your r. And at this point, you will be having your kinetic energy, that is Q value, where the alpha particle escape from the potential value. That is the R. So actually, that is the width of your the potential L, that e raised minus 2 k2L. We already discussed that L is this R0 to R distance. So R, so this limit we have to apply now. Okay, so that will give you ln of t equal to minus 2 times 2me by h cos square plus 1 by 2, and r. Now if you substitute sine inverse, if you substitute capital R, then first term will come as sine inverse of, okay, let's put it that way. So r by r plus root r by r into root 1 minus r by r, and this whole term will be minus sine inverse of root r0 by r, right? R0 by r plus root r0 by r into 1 minus r0 by r. Now this is further reduced into minus 2 times 2me by h cross square all raised to 1 by 2, and that will be r. And what is this? Sine inverse r by r is sine inverse 1, that is pi by 2. And then this term will become 0, because 1 minus r by r will become 1 minus 1. This term becomes 0, and multiplied by this also becomes 0. So these two will become 0, and then we have minus sine inverse of r0 by r here. Okay, so sine inverse of root of r0 by r, and minus, this is also minus root of r0 by r, root of 1 minus r0 by r. So Now what is this? Pi by 2 minus sine inverse of r0 by r. So this will be cos inverse r0 by r, so root of r0 by r. That you can substitute in this expression. Okay. So before that, we can go further. So let's assume let's assume that your R, which is very larger than capital R0, which means that your nuclear range is very small as compared to the potential barrier width. Okay. So when R is very larger than R0, then your R0 by R will be very small than 1. Okay. So what will happen to the pi by 2 minus pi by 2 minus sine inverse of root of r0 by r, that can be approximated because r0 by r is very less than 1 now, which means that you are having very small value here. Okay, so this will result in pi by 2 minus sine inverse of r0 by r when the x, for example, you are having sine x or sine inverse x. When you are having sine inverse of x, when x is very small, sine inverse of x will become x. Okay. So from that we can approximate when you are having this condition r equal to r is very larger than r0, r0 by r will become very small than 1, and in that case your sine inverse of very small quantity will become that quantity itself. So this will become pi by 2 minus root of r0 by r. And similarly in the second term, that is root of r0 by r, this is very small, and also 1 minus r0 by r. So here we have 1 minus r0 by r. So this can be approximated with r0 by r is very small than 1. So this can become 1. Okay. And so this term can become a root of r0 by r. You can also expand this. It is not necessary, but you can do like this 1 by 2. This will be equal to some 1 plus etc. So this term will be very small as r0 by r is very small, and you will be having only uh, one one term here. So that will be multiplied with the r0 root r0 by r, and you will get root r0 by r is 0. Or you can simply assume that this r0 by r is very small as compared to 1, so that 1 minus r0 by r equal to 1. So this will become r0 by r, root of r0 by r under that condition. Okay. So the result will be like you can have some equation number. I don't know which equation number. I have used some. Let's say this as 5, or you can use any equation number in your own way. So 5 will implies again ln of t will become minus 2 times 2 m e by h cross square all raised to 1 by 2 into r times pi by 2 minus root of r0 by r minus root of r0 by r, right? Because this term will become r0 root of r0 by r, right? Yes. So this term also become root of r0 by r. So it will be pi by 2 minus root of r0 by r minus root of r0 by r. Okay. So that can be ln of t equal to minus 2 times 2 me by h cross square all raised to 1 by 2 into r times pi by 2 minus 2 times root of r0 by r. So this is the expression for this is the expression for the transition probability, okay, or transmission probability of the alpha particle by Gamow theory. So this is the transmission probability by Gamow Gamow theory. So this is the transmission probability by Gamow theory. Okay. So what he used, he took the concept of quantum mechanical tunneling to explain the alpha particle decay, and he got this much of uh, probability of transmission through the potential barrier. Okay, and if you further substitute the values of E and R in this expression, for example, let's take for our case, you know that the but R equal to let's take one 2z e square. This we already discussed by 4 pi epsilon 0 e. Okay, so if you substitute this, then you will get ln of t will become minus 2 times 2 m e by h cross square all raised to 1 by 2, and which is multiplied with pi by 2 times r. Okay, so if you take the terms outside, okay, then you can have pi by 2 times your capital R, so that capital R can be replaced with these numbers. So it will be zd square by 4 pi epsilon 0. Again, this will be now it will be added because you are having minus 2 multiplied with the other terms also. So we'll have some quantity like 4 times 2 me by h cross square all raised to 1 by 2 times it will be r0 divided by this quantity, that is 2ze squared by 4 pi epsilon 0 e. Okay, so there will be an e here. This much, this is your r value. Okay, so these two terms should be in root, that is 1 by 2, and this is again multiplied with r. So it is simple concept. Just substitute r value in this equation after taking after opening this bracket. So we have to multiply with minus 2 m each cross square or 1 by 2 into r times pi by 2, that is first term, this term. Then you have to multiply minus 2 m e by h cross square all is 1 by 2 into r into second term, this one. So we'll get minus 2 times minus 2 will get plus 4, and remaining terms are there. Okay, so that is what we have done here. And if you do some manipulation in this equation that you can do by yourself, that you do as a homework. So after that, I mean, after some cancellation and rearrangement of these equations, you can have one equation like there is some constant, that is ln of t will be equal to some constant times z, that is the first term. Okay, so the first term will be having z because you see this is having, I will give you a hand. So this is having e raised to 1 by 2. Okay, e raised to 1 by 2. You are having one e here also. So this will give you 1 e raised to minus 2. Sorry, e raised to minus 1 by 2. And also from here you can have e raised to 1 by 2 here, and in this process. So here you will be having e raised to here all bracket 1 by 2. So this two. So first I will tell first this. positive term first, then negative term. Okay, so it will be something minus the other thing. So this will result in z raised to 1 by 2. That is from the second term. Okay, so there will be a z. Okay, so z terms. Okay, you have to substitute this value also. I did here. You can substitute this r. Forget to do that. Okay, here also you will be having what is that, 2z e square by 4 pi epsilon 0 e. Okay. Uh, okay, so that is your r value, and you'll be having 1 by 2 here. So 1 by 2, 1 by 2 will be here 1. E get cancelled. So you will be having one z. You are having z here. So z raised to 1 by 2 here, and one z here. So that z and this z raised to 1 by 2 will cancel. You will be remaining as z raised to 1 by 2 in this term. And there is one more term which will come as r0 raised to 1 by 2, and all other terms are constant. This e raised to 1 by 2 here, e raised to 1 by 2 here, they will produce one e in the numerator, and you are having one e in the denominator. That they will cancel each other. So there will not be any e term in the second part of this equation. Only there will be one z raised to 1 by 2 and r0 raised to 1 by 2, r0 raised to 1 by 2, and all other terms are constants. Okay, so that is replaced with a. And then we have minus. I'm taking this minus term second. Okay, then we are having here one e in the denominator, one e raised to 1 by 2 in the numerator. So that will give you e raised to minus 1 by 2. And what is then you are having only z. Okay, z here. So you can write z here, then some constant b. That b is nothing but all other constant values. So this you can get when you consider when you substitute the r value for in the Geiger-Nuttall transmission equation. Okay. So this a value, which is a constant, which is approximately equal to 1.29, you can refer that. And this b is 1.72. You refer these two numbers, how much it is coming. And all these terms are z raised to 1 by 2, r0 raised to 1 by 2. These terms will depends on your nucleus, what nucleus you are using. And it depends on that, your atomic number will be different, your range will be different. So that is dependent on different nuclei that you are using. So the transmission probability of the alpha particle from that particular nuclei will be depending on the atomic number. That is the number of protons and the energy E of that alpha particle which is coming out, and it also depends on the range of that potential value. So, sorry, the nucleus, range of the nucleus. So it depends on all these factors. Okay. So and a constant, two constants. So it depends on these factors. The probability of alpha particle to come out of that barrier can be calculated by using this equation. Okay, so that's about the Gamow theory. Okay, Gamow theory of alpha decay. And when this Geiger and Nuttall, that when they experimentally studied the relation between uh, the half the energy, that is the energy of the alpha particle, and the decay constant of that particular nuclei. Okay, so Geiger and Nuttall, you can verify this spelling. Geiger and Nuttall's law, what they did, they experimentally studied the relation between the disintegration constant, okay, or this decay constant, and the alpha particle energy. So when they observed that, they have observed there is a decreasing of decay constants when you increase the energy, or the alpha. If the alpha particles are larger, then the decay constant will become small and small. Okay, which is very simple concept here. So uh, uh, actually, these people experimentally studied that how the decay constant related to the alpha particle energy, and they observed that when you are having alpha particles with very large energy, that is the alpha particle coming out of the alpha decay process, which is having alpha energy, that is kinetic energy, which is larger, then that kind of nucleus will be having smaller decay constant, or the decay will be small. Okay, decay disintegration constant will be small. In the same concept, in the same way, if the energy is small, then they have very large decay constants. Okay, that is what they have observed. So that can be represented uh, I don't know how it will come. Let's say, okay, here and okay, almost like so. In this case, we'll take log lambda versus um, I have to take the um, in this axis it is energy, so it will be z by root. Okay, okay, so when we increase the z by root e, okay, so this is like this curve will give you like this. If you take in logarithm scale, it will be like this. So this can be again found. Okay, this is so yes. When you are increasing the energy here, when you are increasing energy, which means that your this value z by e value will be less. Okay, so for example, we take this point. So here you will be having energy which is smaller as compared to. So, no, this part you will be having energy which is higher as compared to this portion. Okay, so here we will be having energy which is small. All right. So when you're having small energy, the disintegration constant is small, right? Yes. So when you're having small energy, you will be having disintegration with constant which is small. When you're having higher energy, which means that z by root e, which is smaller, then you will be having higher disintegration constant. And this is the Geiger-Nuttall's law experimentally, but this is the theoretical graph that we can say. Let's take the T as your uh, probability, transmission probability, transmission probability. Okay, so then if you consider the alpha particle, so this already formed in the alpha particle. Actually, the reality in reality how it is coming out, because your alpha particle is already there inside your nucleus. Okay, so there is a high potential barrier to cross this nucleus, so it always try to move back and forth, and it will try to collapse these walls of nucleus, and it will try to escape from the nucleus always. Okay, and it says it is around 10 raised to I think it is 10 raised to 21 times per second. It will collide with this. walls of the nucleus. So it will always vibrating or trying to escape from the nucleus very fastly. So it is almost 10 raised to 21 times per second. It will collide with this potential barrier of the nucleus. So it will be always vibrating and it is always trying to escape from the nucleus. So this much of times it will hit the walls or the barrier, it will try to escape from the nucleus, and the probability to escape is also 10 raised to minus 21. That is another factor. So that is not important. I'm just saying how much uh, how it look like exactly. So it will always try to vibrate, it always try to escape from the nucleus with 10 raised to 21 times per second. It will hit this potential barrier and nucleus wall, and it will not escape. The probability is only 10 raised to minus 21 to escape from the nucleus. And because of this, we can say that the frequency of collision of this alpha particle will be nothing but let's say it is nu, which is nothing but if you are having a velocity v0, then you will be having that 2 r0. So this is very simple. If you are having r0 as your range or the radius of the nucleus, then you are having 2 r0, which is the path length that you can see from here. And that is you know that t will be equal to v, what is that, x equal to v by t, x equal to v by t, so t will be equal to v by x, right? So in this case this is right, t v equal to x by t. Let me see. Okay, so it will be inverse. So this is x and this is v. Okay, so t equal to x by v. Okay, so which implies you 1 by t equal to v by x, and 1 by t is your frequency, and this is equal to v. If the velocity of this particle, which is moving, this alpha particle moving inside the nucleus, is v0, then it will be v0 by x is nothing but the distance to r0, that is this. So that is the frequency of collision, and the transmission probability if we take t as t, and the radioactive decay constant. From that we can have the radioactive decay constant lambda, that will be equal to nu times t. That is the probability times the frequency. That is how much times the alpha particle hits on the walls of nucleus times the transition probability will be your disintegration constant or decay constant. So from that, if you take the logarithmic value of this, okay, uh, so there is also this v0. We can approximate v0, which is having some 2 into 10 raised to minus 27, 10 raised to 7 meter per second. That is velocity. Whatever it is. So if you substitute that range 10 raised to r0 equal to 10 raised to minus 15 here, then you can see that nu, you know what is nu, and can cancel out that 21 with this value, then you get this minus 7. So whatever it is. So here we'll be having decay constant, which is nu times transmission probability. So if you take log of that, log of lambda will be given by log of nu, log of nu, then will be plus log of t. Okay, this is product, so you can write it like that. So this term we already calculated previously, so we can have log of lambda will be nothing but log of what is nu is v0 by 2 r0 plus what is this term, log t. Log t is we already calculated, which is 1.29 times z raised to 1 by 2 and r0 raised to 1 by 2, and this is minus 1.72 times what is that, z raised to minus 1. Okay, so from this itself we can after substituting the gamma theory of alpha decay values, then expression, then we can easily calculate what is the relation between the lambda and the energy, because this term is a constant. Okay, so from this also, if you consider only energy part, then this also we can take as a constant. So this whole term become constant if you consider energy as varying, because we are taking energy variation here. Okay, and z also we are having variation in z also. So this can be replaced with lambda, log lambda equal to some constant a. Let's take this term as minus value. So we can say for a particular z value, this term, first term we can take a1. So this term we take first the positive term and then the negative value. So okay, let's take in this way. So this one a1, let's say minus a1, this term we are talking. So it will be minus a1 times z by some, what is that, z times root e, right, plus a2, this is constant. So this is the expression that we have used to draw this particular curve, log lambda versus z by root e. Okay, so this will be shifted by a factor of a2. Okay, and with this will be your slope. Okay, this slope will be equal to, now this slope will be equal to minus 1.72. So this constant value that you used for gamma theory also can be found after experimental calculation of disintegration constant versus z by root e. If you calculate that, then you can also get the value of this constant here. Okay, so that is the slope of this curve. So from this we can see that the disintegration constant is actually varying when you're having more energy which is larger disintegration constant. When you're having smaller energy, you'll have a very small disintegration constant. Okay, so from the Geiger-Nuttall's law, you can further relate this Geiger-Nuttall's law from let's say further says that they have the alpha particle, the kinetic energy of alpha particle, how the kinetic energy of alpha particle is related with the half-life of, that is t half. Okay, that is half-life of that nuclei. So this is the study also given by the Geiger-Nuttall, how the alpha particles kinetic energy, which is related with the half-life of uh, the nuclei. So that this is similar, because when you're having lambda value, you can easily calculate what is t half. T half will be nothing but 0.693 by 0.693 by Okay, what is that? Lambda. Okay. So from that we can see if lambda is larger, which means that T half is smaller. Lambda is larger, then T half is smaller. So from this we can say that by Geiger-Nuttall's law we can have the relation between the half-life and the kinetic energy of the alpha particle which is coming out. So if you increase the kinetic energy of alpha particle, your z by root e value is decreasing, okay, and which will result in increasing your lambda value, okay, which means that when you're having smaller kinetic energy of alpha particle, which means that they have higher disintegration constant value, and which results in T half which is smaller. And when you're having E which is smaller, then you'll be having Z by root E value which is higher, which causes lambda which is small, and your T half will be higher. So when you're having lambda which is smaller and T half, so this relation is experimentally provided by Geiger and Nuttall's law. The relation between T half and the energy by calculating how the disintegration constant is related with the transition, sorry, the energy of the outcoming alpha particle. Okay. So this is what Geiger-Nuttall's law says. If you are having higher energy or higher kinetic energy alpha particle which is coming out, then they will be having smaller half-life. If you are having smaller energy, then they will be having higher half-life. This is very easy to understand from the previous figures. I don't know whether I will check that that figure. What is that? It is not that. Okay, so I will draw it again a little bit. We already had some discussion on it. But let's say. So I should have copied something. So here, let's say, oh, that's good. Not bad. Okay, so if you consider the potential well and all those things, then we can have. I'll take one color here for explanation. So you'll be having the potential which is varying like this and coming back like, and we'll be having some 25 mega electron volt of potential barrier, and which is decreasing 1 by R fashion. Whatever it is. So let's say if you are having your alpha particle is having energy which is in this range, the alpha particle is having energy in this range, for example. Okay, another alpha particle which is having energy, I will take one another color to explain this. So another alpha particle which is having energy which is in this range. This is just an example. So normally it will be in 4 to 9 mega electron volt. So this is just an example. So this alpha particle which is having more energy, because this is Q value will be higher. Let's take this energy as E1 and this is E2, which means second one is E2. Then we take that E1 is larger and E2. From this potential curve we can easily understand that energy is higher in E1, energy is smaller in E2, and these are the two alpha particle which is coming out. For example, first case we are having a reaction like this, X into Y, and that will plus alpha particle with energy E1, and another reaction X dash gives you Y dash plus alpha particle with energy E2, and your E1 is greater than E2, which means that then we can calculate which reaction is having more half-life and which reaction is having less half-life. So from this curve, we can calculate this from this energy of the output alpha particle. We can easily say that this T half is smaller and the other one is larger and those things. So that is experimentally verified by Giger and Nuttall, and they have given these relationships, all those things. And from this curve, we can easily understand that because when you are having E1, which is larger, from this curve we can see this alpha particle can easily penetrate this potential barrier, which is because the width is very small and which can come out of this potential barrier. But if you consider the second case, in the second case, we are having large potential barrier here, so it has to cross a little more, so it has to go exponentially decreasing like this, and it will almost reach, okay, it will almost reach at this point. So it has to cross very large, width is very large here, okay. So the probability of transmission in this time, which will take more time, okay, in this case. So in the second case, this will take more time as compared to this will take very less time because the potential barrier width is very small here. Why? Because you are having more energy. So if you are having higher energy, your time to cross this barrier will be smaller, and if you are having less energy, kinetic energy of alpha particle is, if it is less, then it will take more time to cross that barrier. So this case we will have T half which is larger. In this case we have T half which is smaller. So that is the result of the Geiger-Nuttall's experimental verifications. So that is the concept of Geiger and Nuttall's law. When you are having higher energy of alpha particle which is coming out, you will be having smaller half-life of that reaction. And if you're having smaller energy, you will be having higher half-life for that particular gamma alpha decay process. Okay, so that's all about the alpha decay process. Now we will move to the beta decay process.